So the title of this paper is 1-1 Constraint Pseudorandom Functions. I'm Rotem, and this is a joint work with Naty and Hoeteck. So in this talk, I will first give you the definition of 1-1 constraint PRFs, and then I will go over the results in the paper. So we have both some constructions of 1-1 constraint PRFs and also one lower bound result. And in addition, we have a few applications for it. So I will go over all of that in the talk, but let's first start with the definition. So in a 1-1 constraint PRF, we consider two parties, Alice and Bob, and both of them share some common random string that we denote by some capital K. And in addition, Bob has a value X and Alice has some policy F. And this policy F takes any possible input and maps it to either 0 or 1. So if it maps some X to 1, we say that it authorizes X. Now, given this setting, each of them computes independently some function. So Bob takes his input x and the CNRS k and computes k sub x. And similarly, Alice takes her policy f and the CNRS k and computes k sub f. And we want those two values to have the following relation between them. First of all, we want that if f authorizes x, which means that f of x equals 1, then given k sub f, it is possible to reconstruct k sub x. So another way of saying this is that k sub f encodes in it all of the values k sub x for all of the x's that are authorized by f. On the other hand, for security, we want that if x is not authorized by f, then even given k sub f, the value k sub x looks uniform. It is distributed uniformly, even given k sub f. So I want to also suggest an alternative definition, which also hints on why we chose to call this 1-1 constraint PRF. So let me first go over what a constraint PRF is. So in a standard PRF, we have a seed. And given this seed, it is possible to compute the pseudorandom function on every possible input. But for the person who doesn't see this seed, even if he sees many evaluations on the function, he cannot distinguish whether they were computed with the seed or whether they are just uniformly sampled values. So this is a standard PRF. Now in a constraint PRF, in addition to this seed, it is also possible to compute a constraint seed. And the constraint seed is described by some function f. And this function f determines on which inputs of the function the constraint seed can compute the PRF. So given a constraint seed for f, it is possible to compute the PRF only on inputs x that are authorized by f, but evaluations on other inputs, on x's that are not authorized by f, still look uniform even given the constraint seed for f. So if we look at this constraint PRF primitive, and now we restrict the adversary to only see a single constraint seed and also to only see a single evaluation of the function on some input that is not authorized by the seed, then we get exactly the setting that you can see on the slide here, the setting of the 1-1 constraint PRF. So 1-1 denotes that this is a constraint PRF where the adversary can see one key and also one evaluation. Now, in pseudorandom functions, we always think about computational security. Because we cannot hope to get real randomness, otherwise we wouldn't need the pseudorandom function. But now, because we only require uniformity with respect to a single value, to a single case of x, it actually makes sense to consider perfect uniformity and not pseudorandomness. So let's begin with the first construction for the equality function class. So in this setting, the input space is subfield f, and then every function is also characterized by some value from the field. And every function f sub x prime accepts only the single input x prime. So it takes as input x and it outputs 1 if and only if x equals x prime. So here is how the construction would look like. In order to generate the common reference string, we sample a random linear function over the field. So this is equivalent to sampling two random values in the field. And now whenever we want to compute k sub x, or whenever we want to compute k sub f of some x, we would do the same thing. We simply evaluate the random linear function over the corresponding inputs. So we compute, we take the input x, we multiply it by k sub 0, and then we add to it k sub 1. So of course, for correctness, if x prime equals x, then k sub fx prime would be exactly k sub x. So in particular, it allows to compute k sub x. But for security, as long as the adversary can only see the evaluation of this linear function on 2 points, he cannot tell whether they were computed according to the predetermined function or were just sampled randomly. So even given one of the values, he cannot tell whether the other value is truly random or not. And this construction can actually be generalized if you want to support more than a single key or more than a single evaluation, but as long as we have a constant number of them or a predetermined number of them, then we can simply start with this from a CNRS that is some random polynomial of a specific degree. So if we want to allow up to t number of keys or evaluations, we can start with a polynomial of degree t minus 1, and we would be fine. Okay, so now let's see another construction. So we consider the subset functionality. In this setting, we have some set of size n, and we define the input space to be all of the possible subsets of those n elements. So the input space would be of size 2 to the n. And in addition, we also characterize every function that we want to support by some subset of the same n elements. So every input is a subset and every function is a subset. And now we define that the function of some subset x prime accepts the subset x if and only if x is a subset of x prime. So every function is described by some subset, and it accepts all of the subsets of this subset. So let's see a construction for this function class. So for every of the n elements, we sample a random value, k sub I, and we let all of those n values together form the CNRS. And now, suppose that we get some x, and we want to compute k sub x. So recall that x is a subset of those n elements. So for every element that appears in x, we take the corresponding k sub I from the CNRS, and then we XOR all of those values together and let it be the k sub x. And when we want to generate a constraint key for some subset, then again, we take all of the k sub I that corresponds to this subset, but now instead of XORing them, we simply give all of them. So the person who sees all of the k sub I for some subsets that corresponds to f can now take any subset of this subset and compute the corresponding k sub x. But for security, once he tries to compute k sub x for another value, then this k sub x is completely masked by some k sub I of a value that does not appear in the key. So we get both correctness and security. So let's see now the third construction for the inner product functionality. So in this functionality, the input space is length n vectors over some field, and every function is also associated with some length n vector y, and we say that f of y accepts x if and only if the inner product of y and x is 0. And here is how the construction would look like. So in order to sample the common random string, we look at length n random vector v, and in addition another single random element w. Now we define k sub x for every x to be the inner product of this random v from the CRS with x. And in order to generate a key for y, we consider w, the single field element, multiplied by y, and then the vector v added to it. So let's see what happens when I try to reconstruct k sub x. So suppose that I have the key for y, k sub y, and now I take the inner product of k sub y with x. So I will end up with the inner product of v and x, which is exactly k sub x, the value that I'm trying to learn. But then it is masked with the additional field element that is determined by w multiplied by the inner product of y and x. So if the inner product of y and x is 0, then this mask will be 0, and I'm fine, I can learn k sub x. But if it is not 0, then the w element and its uniformity guarantees that I will end up with a value that looks completely random. So we get exactly the correctness and the security properties that we need. So as a last observation, we also want to mention that given a 1-1 constraint PRF for two different family functions allows me to get 1-1 constraint PRF for the following new family functions. So I can concatenate any function from the first family with every function from the second family, and I can connect them via an AND gate. So as long as x satisfies both the first function and the second function, then it is authorized by the new composed function. Okay, so now let's see the negative side of things, even though I think that this lower bound is interesting, so it's not so bad after all. So recall that we had this trivial construction, which allows us to support any function class, but with the price of having keys that grow with the input space. So our next observation is that for some function classes, this is the best possible. And in particular, we will show this for the inequality class of functions. So here, every function is described by some element y. And then this is a function that is punctured on this point y, in the sense that it accepts all of the inputs except of this specific y. So inequality functions are included in NC1, so it means that we cannot hope to get a generic construction for 1-1 constraint PRFs for NC1, which is efficient. So let's see the high-level idea in the proof. Okay. So consider some x and look at the constraint key for f of x. So due to the correctness, we know that this key should allow to compute k of x prime for all of the x primes which are different than x, because all of those x primes are authorized by f sub x. But on the other hand, due to the security, we also know that k of fx shouldn't reveal any information about k sub x. So it means that k sub x must have at least a single bit of entropy, even given all of the other k sub x prime, for all of the other possible x prime. So keep that in mind. And now consider some other value, y, and look at the constraint key for f sub y. So again, because of the correctness, we know that this key for f sub y allows to compute k of x for any x that is different than y. So in particular, it's for almost the entire input space. Those are many different values. But because of the first fact, we know that each of those values must have at least a single bit of entropy, even given all of the other values in this set. So because k of fy allows to compute all of those values, and each of them must have at least a fresh bit of entropy, even given all of the others, it means that k of fy must include in it at least a single bit of independent data for each of the values that it allows to compute. So it means that the size of K for Fy must be as large as the input space. And those kind of properties we already get from the trivial construction. So in some sense, this is the best we can hope for. Okay, so now let's move on to some applications. So the first application would be the following. So suppose that we have a 1-1 constraint PRF star, which I will explain in a minute what I mean by this star. And in addition, we have some key homomorphic PRF, which I'll also explain in a minute what it means. Then we can get a standard constraint PRF for a single key, which means that we can move from the single query to polynomially many queries, like in any constraint PRF. So what is a key homomorphic PRF? It's a PRF that allows you to perform homomorphic evaluations over the seed. So if you think about it for a while, it only makes sense to consider linear computations. Otherwise, it would break the pseudorandomness of the PRF. So that's the requirement. We want a PRF that if I have an evaluation with the seed A over the input X, and I also have an evaluation with the seed B over the input X, then if I sum them up, I will get a value that is equivalent to the value that I would get if I was first adding the seeds and then computing the PRF on X. And that should also work with multiplication by a scalar, so any linear evaluation over the PRF seed. So now what do I mean by 1-1 constraint PRF star? So I want my 1-1 constraint PRF to have some spatial security property, which is the following. So I want to have a simulator that takes f, and then it generates two strings. One is k sub f, which would be identical to the standard k sub f that I would get in the real to the standard k sub f that I would get in the 1-1 constraint PRF. But in addition, I also want to get another value that I call here k hat of the complement of f. And this special value needs to have the following two properties. So first of all, I want this k hat to be distributed uniformly, even given k sub f. So this is similar to what I previously required from k sub x for x that is not authorized by f. And in addition, I want that this k hat would allow me to compute k sub x, but only for x that are not authorized by f. And I want this computation to be linear. So instead of now requiring this randomness with respect to every k sub x that is not authorized independently, I require that there would be like a single seed, this k hat of the complement of f, which first of all, looks uniform, even given k sub f, and second of all, allows me to compute k sub x for all of the k sub x that are not authorized. So, in fact, it turns out that all of the constructions that I discussed previously, they satisfy this property. So you can see that in the full paper. I will not go over it here again, but it's pretty simple to see. And I will also not go into the technical details of the construction, but I will give you a hint, and it's pretty straightforward from there. So I start from a key homomorphic PRF, and whenever I want to compute the PRF on some value x, I first use the 1-1 constraint PRF to compute k sub x, and then I use this k sub x as a seed to the key homomorphic PRF, and then I evaluate this key homomorphic PRF over the input x. So in the security proof, I can rely on the randomness of this k hat, and then to claim security of the key homomorphic PRF with respect to the seed k hat, and to perform homomorphic evaluations over it in order to reconstruct the PRF evaluations. So that's it about the first application, and I just want to mention that in other literature about constraint PRFs, it's common to consider the setting where there exists a single key. So let's move to the second application. So now we consider CDS, conditional disclosure of secrets, which is also a primitive that has various applications. So let's go over the definition of CDS. So again, there are two parties, Alice and Bob, and they share a CRS K, but now in addition they also share some secret S. And I consider some policy G that appears in the sky, or both also know the policy G. And in addition, each of them has some input. So Alice has Y and Bob has X. And this policy G, it maps every pair of X and Y to either 0 or 1. So again, each of them now, given all of the values that he sees, computes an additional value. So Bob takes X, K, and S and computes K sub X, and similarly Alice takes K, S, and Y and computes K sub Y. And now I'm being not very formal, but we want to have the following property, that given Kx and Ky, the following happens. So if G of xy equals 1, then it is possible to reconstruct the secret S. But if G of x and y equals 0, then S looks uniform. S looks as if it was distributed uniformly, even if you can see Kx and Ky. So now our next observation is that those 1-1 constraint PRFs imply CDS in a very natural manner. So let's see again on the right-hand side the definition of 1-1 constraint PRFs. So what are the differences? Here we don't have a secret. Here, instead of having the policy in the sky, we let Alice choose the policy. And in addition, Alice does not have the value y. So given this 1-1 constraint PRF, here is a very natural way to get CDS. So we want to use the pseudo-randomness of K sub x in order to hide the value S. So what Bob would do is that after computing K sub x, he would XOR it with the secret S, and then that's the value that he would output in the CDS. And for Alice, so now she knows the value, the function g that appears in the sky, and she also has her partial input y. So she would consider the policy f, which is the function g with y hardwired in it, and that's the function for which she would compute the 1-1 constraint PRF. So now, given those two values, which are denoted in red on the slide, so if x satisfies g with respect to y, which means that if g of y and x equals 1, then given this k for g and y, it is possible to reconstruct k sub x, and then given the value that we received from Bob, we can learn S by XORing it with k sub x. But on the other hand, if the value of g of x and y equals 0, then it means that k sub x looks uniform, even given the value that was received from Alice. And therefore, the value that was received by Bob is also completely masked by k sub x, and in particular, it hides S. So for those of you who are familiar with attribute-based encryption, you can think of as CDS as the single key, single ciphertext information theoretic variant of ABE, and then this 1-1 constraint PRF, the single key, single evaluation information theoretic variant of constraint PRF, and then the same way that we can go from constraint PRF to attribute-based encryption, we can also go from 1-1 constraint PRF to CDS. So that's about it for the offline session, and of course feel free to ask questions in the online session or offline.